Finding trigonometric ratios in the Cartesian plane. We have dealt with problems solving for acute angles, the angles within a right angle triangle. However, what if we are required to solve angles other than acute angles? In other words, obtuse angles, reflex angles, and negative angles. To do this, we'll make use of a Cartesian plane. Now, if you haven't noticed, all of the angles that we use to solve for missing sides or missing angles were acute angles. You can see all of these problems, angles that are less than 90 degrees. All of these angles that we outputted were less than 90 degrees. They were, in other words, acute angles. Now, what if we require to do calculations for angles bigger than 90 degrees, like 170 degrees, or 235 degrees, or 195 degrees? How do we perform these calculations? We do that by making use of the Cartesian plane. Now, this is a very big topic. It's a very, very big topic. In my first year at university, more than 85% of the students failed applied physics, which was heavily dependent on trigonometry because they didn't understand this simple fact. Is that when we use a Cartesian plane, we orientate an object in space. So from being random in space, we locate it precisely. Okay, as I've explained before, I could have a page here, right? And on this page, I can draw a point. Where that point is, how far it is from some other point, and where it is located, we don't know. But if I put a Cartesian plane on this page, then I can locate that point precisely because we have x and y coordinates. So relative to what we call the origin, we can find out how far left and how far up that point lies from the origin. And what's the beauty is that I can take this Cartesian plane and place the Cartesian plane right at the edge of this page here. And I can also do the same thing, find out how far left, how many units left, and how many units up does that point lie relative to the Cartesian plane. So that's the importance of using a Cartesian plane. Now with using it, although it's convenient and more accurate to use a Cartesian plane, it also means that when we output answers, we have to locate the point precisely in space too. So let's say that I was not given this point, I found that point. Then I need to tell the examiner how far to the right of the origin it is and how far up from the origin that point lies. Understood? So the primary purpose of using the Cartesian plane is to locate a point precisely in space. So on that page, we need to locate it precisely. However, when we're using a Cartesian plane and we locate a point using it, we need to tell the examiner where that point lies. Because that was the primary purpose of using the Cartesian plane to even begin with. So, in other words, what I'm saying is, we need to give both the magnitude and the direction. These are two important words. Let me illustrate this to you. I have a page here, right? I have a page. On this page, I draw a Cartesian plane. Because why? I'm using it to locate a point. And let's say that we have this point here. I can say this point lies 3 units to the right of the origin and 4 units up. So 3 units, there's the origin here. It lies 3 units to the right and 4 units up. So it'll be 1, 2, 3, and 1, 2, 3, 4. So at this point here, I move 4 units up and 3 units to the right. That's how we'll locate that point. We can do two things. We can say that this distance here is equal to 3 units, and we can say that this distance here is equal to 4 units. So if I take a ruler and I measure, that will be 3 units long. This will be 4 units long. But when I'm using the Cartesian plane, I need to state direction. So the way I'll do that, I'll say plus 3 units and plus 4 units. This plus sign here is used to show the direction. So this is how we indicate the direction. We indicate the direction using the negative and positive axes. Because we know to the right of the region we have positive x. And to the left of the region we have negative x. So what we're saying is, although we know the side is 3 units long, so we know that the side is 3 units long, but when we're trying to locate the point, we have to say plus 3 units because that plus says that we're moving to the right 3 units. Because you could also move to the left 3 units, that would mean minus 3 units. But since that point lies in the first quadrant, where x is positive, that's why we move 3 units to the right. So what I'm saying is essentially, right, if I have to put this idea completely, I could have had the side here 3 units, I could have had the side here 4 units, and I could have made a right angle triangle here. This right angle triangle lies randomly in space. But if I take it and I put it here at the origin of the Cartesian plane, then I'll be able to locate that point precisely. That's the reason why we use the Cartesian plane. Because from having an object being randomly positioned in space, I can locate it precisely by using the origin as a reference point. Understood? So 3 units to the right, 4 units up. So in quadrant 1, we say x is positive, y is positive. This is quadrant 1. In quadrant 2, we say x is negative, y is positive. In quadrant 3, we say x is negative, y is negative. And in quadrant 4, we say x is positive, y is negative. Now, this will make a lot of sense when we start delving into much more in-depth questions. Yeah, so there's it here, shown graphically. X positive, y positive, x negative, y positive, x negative, y negative, x positive, y negative. Right, so as I've said now, when we're using the Cartesian plane, we need to indicate both the magnitude and the direction, because that's what the Cartesian plane enabled us to do initially, is to give us the precise location of a point. How do we give the precise location? Is by giving the magnitude and the direction of that point, right? And how far it is from the origin. So how does the Cartesian plane enable us to solve for angles other than acute angles? Because see, acute angles will be for angles between 0 and 90 degrees. 90 to 180, 180 to 270, and 0 and 360 is the same. Right? So how does it... So this, we solve for angles only in this first quadrant. What the Cartesian plane enables us to do is it enables us to solve for angles like this angle. This angle here is bigger than 90 degrees. It enables us to solve for angles like this angle. This angle here is bigger than 180 degrees. It enables us to solve for angles in here, because this is even bigger than 270 degrees. And how? How does it enable us to do that? Because if I can take any random point in any quadrant, and if I drop a vertical line to the x-axis, I form a right angle triangle. This enables me to do two things. It enables me to define how many units to the left or to the right of the origin does this point lie, and how many units up or down does this point lie from the origin. And what does that enable me to do? It enables me to give both the magnitude and the direction. Now I'll show you exactly how we can do that, but I just needed to prove to you that when we use the Cartesian plane, show both the magnitude and the direction. And how does the Cartesian plane enable us to solve for angles other than acute angles? By using the simple fact that if I take any point located in any quadrant, as I've shown here in figure 2, I can drop a vertical line and I can form a right angle triangle. See, this vertical line is vertical to what? The Cartesian plane. It's parallel. And since this is 90 degrees, this has to be 90 degrees. Understood? At any quadrant, they have proved it here, right? So knowing that, and knowing that in different quadrants, x and y values change, it's either positive or negative, then we can move on to something very important. Recall that the right angle triangle trigonometric ratios are defined as follow. We define this ratio for a right angle triangle in quadrant 1. Sin theta is equal to y over r, sin theta is equal to x over r, tan theta is equal to y over x. Since we have direction and position, this means that the values that sine, cos, and tan and their reciprocals will output in the Cartesian plane will be different in each quadrant. Now listen to what I said. I said since we have direction and position, both means the same thing. Why did I say that? Because we are using the Cartesian plane now. So since we are dealing with direction and position, the values that the sine, cos, and tan output in different quadrants will be different, because the x and the y's will not be the same in different quadrants. Like in quadrant 1, x is positive and y is positive. In quadrant 2, x is negative and y is positive. Okay, and then remember that r will always be positive because of the theorem of Pythagoras. Therefore, the sign of sine and cos and tan will be dependent on the sign of the x and the y axis. So if you look here, we have some right angle triangle here, right? We have some point P there, which has x and y as the coordinates. Therefore, this is x, this is y, that is r, right? Remember when we defined it with a circle. That's how it was defined, and r refers to the radius. So the radius is equal to the square root of x squared plus y squared. Therefore, what we have is some positive value, and this value will always be positive because we're referring to a distance. So what's the distance from here to there? Understood? That's the reason why sine and cos and tan will only change according to x and y. Because here you'll always have a positive r. R will always be positive. But what changes? It's the x and the y. So if you have a positive over a positive, then overall that'll be positive. But if you have a negative over a positive, then overall that'll be negative. Understood? So that's the reason why the value of these trigonometric ratios in different quadrants will be dependent on the sign of x and y, is basically what we are saying, right? So therefore we say in quadrant 1, sine is positive, cos is positive because it's a positive over a positive, tan is positive. In quadrant 2, sine is positive, cos is negative y because the x is negative, and tan is negative y because the x is negative. In quadrant 3, sine is negative y because in quadrant 3, remember, we're in the negative x axis there. In cos will be negative y because we're in the negative x axis, but tan will be positive because both y and x is negative. In quadrant 4, sine is negative, cos is positive, and tan is negative. Right, so therefore what this enables us to do, in quadrant 1, we know that all is positive. In quadrant 2, sine is positive. In quadrant 3, tan is positive. And in quadrant 4, cos is positive. So therefore we can use a neat mnemonic called the cast diagram, starting from quadrant 4, 1, 2, and 3. And what this enables us to do, it tells us which ratios are positive in which quadrant. Right, so from this we can conclude that when we orientate a point with the Cartesian plane, let me repeat that, it's a very important fact. From this we can conclude, when we orientate a point with the Cartesian plane, in quadrant 1, all ratios are positive. In quadrant 2, sine is positive. In quadrant 3, only tan is positive. In quadrant 4, only cos is positive. This is represented by the cast diagram, represented by figure 3 below, as I've shown you here. Right, so that's very, very important, knowing that. So whenever we use the Cartesian plane, we need to think about these facts, that all the ratios are positive, sine is positive, tan is positive, and cos is positive at these respective quadrants. As I've stated, that in order to solve for angles that are other than acute angles, we will make use of the Cartesian plane. Now, how do we do this? How do we calculate the actual angle? If I have any random point, then I can create a ray from the origin of the Cartesian plane to the point. And as we discussed, if we draw a vertical line from the point to the x-axis, we form a right angle triangle, irrespective of which quadrant the point lies in. I've already explained that point extensively. If I have any random point, this is why we can generalize now. Any random point. There's no limitation. Can be any random point. All I have to do is just drop a vertical line and I'll be able to form a right angle triangle, irrespective of which quadrant the point lies in. And this is why it's so powerful using the Cartesian plane, because there's no limitation with it, right? And what's even more powerful is that the fact that I'm using a right angle triangle, what can we use? The trigonometric ratios, because the primary criteria that we need to satisfy is that the triangle has to be a right angle triangle in order for us to utilize the trigonometric ratios. Okay, I just really want to drive a point home, right? When you're looking at all of these signs, as I've stated, these signs are merely for direction, because when we utilize the Cartesian plane, we must ensure that we state both the magnitude and the direction. What these signs are doing is it's showing you the direction of whatever we are talking about. It's showing you the direction of this point, where that point is located. So when you're looking at this plus and these minus signs, it enables you to get the directions of these points, right? So when you start looking at it from a practical standpoint, don't think of like, what's the point of having this negative sign or this positive sign? That merely shows you the location of the point. Now, where does it lie? Does it lie in third quadrant, fourth quadrant, or second quadrant? Understood? So that's the reason why we need to look at it from a practical standpoint. So the signs are for the direction. The number, the numerical value that you get is what? The magnitude. The numerical value, irrespective of the sign, the numerical value on its own will give you the magnitude. How much of whatever we're talking about. Okay, let's say that we're trying to solve for this x here, and we get x is equal to plus 3. This positive represents the direction because it's going in the positive x direction. But by how much? Give me the numerical value by how much? By 3 what? 3 what? 3 centimeters. So what I can say is that the distance is in the positive direction, and the measurement, if I take a ruler and measure from year to year, it is 3 centimeters. Understood? So by how much and from where? So it's 3 units or plus, meaning to the right, by how much? By 3 units. Magnitude, direction. Magnitude, direction. Very important. So when we get into more practical problems, you need to start thinking like this. This is the magnitude. This is the actual physical measurement of it. And this is telling you where about. This is telling you by how much and where about. By how much and where about. And remember, this where about is relative to the region. Right? Relative to the region. Right. So let's solve a problem so that all of this ideas, understanding why we have to state that sine is positive, tan is positive, and cos is positive. Right, let's look at this question.